it is a great pleasure for me to introduce today our speaker, Professor Ivan Losev. He got his PhD under the supervision of Professor Vinberg in 2007, and then he moved to the States. He worked in the Massachusetts Institute of Technology, then as an assistant professor, as associate professor at Northeastern University. Then he actually moved to the University of Toronto, where I am right now. And currently, so later he joined Yale University as full professor. He's famous for his work in the representation theory. So please take it away. Thank you.
Thank you, Koля. Thank you guys for having me. It's indeed a special occasion. So Vinberg was my doctoral advisor long time ago now, almost 20 years. And the stuff that I'm going to talk about actually traces back to the time when I was a grad student at Moscow. So I think it's an appropriate topic for this talk. And somehow the talk is going to consist of three parts. Well, 2 or 3 parts. First, I'm going to give some general discussion of unitary representations. And this is going to serve as a motivation for the second part, which is the main part, where I am going to talk about quantizations and their representations. And if I have time in the end, I'll talk about this more mysterious topic, unipotent representations and symplectic duality. And I just provide some references, I imagine, so I will be able to post the notes. So you guys will have references for this talk. Great. So let's start. I start with a Lie group G sub R. That's a real Lie group. And a basic question in representation theory is to understand the unitary representations of this Lie group G. So what does one mean for this? G sub R is a topological group. I can consider its topological representations in a Hilbert space. And this representation is unitary if the group acts by unitary operators. Then, you know, as any such representation, this one is going to decompose into some kind of direct sum of irreducibles, where irreducible means that I don't have a proper closed sub-representation. Okay? And then the question of understanding arbitrary unitary representations reduces to classifying the irreducibles. And the most interesting case of a group is when the group in question is semi-simple. That's kind of the most interesting from many perspectives class of Lie groups. And that's what I'm going to assume. And just to give you a very cheap and easy example, if your Lie group is compact, then actually every irreducible unitary representation is finite dimensional, and every irreducible finite dimensional representation is unitary. It has invariant Hermitian scalar product. Since I'm talking about semi-simple groups, I need to recall some basic constructions for them. So I start with a G sub R, and the classification is known, kind of easy special cases will be SLN R or SLN C. So this is a complex Lie group, and so in particular it can be regarded as a real Lie group. Then I can consider the Lie algebra, small g sub R, and I can complexify it and get a Lie algebra over the complex numbers. So when your group was SLN R, this complexification is just Lie algebra SLN C. So this examples are marked in brown. But when your Lie algebra is SLN C, so when your initial group is SLN C or any other complex group, the complexification of its Lie algebras is just 2 copies of the initial Lie algebra. So for SLN C, I will just get 2 copies of the Lie algebra SLN. Then I can consider the maximal compact subgroup. For SLN R, this is SON R, and for SLN C, it's SUN. I can again consider its complexification, capital K. And it's Lie algebra, so this funny symbol is German K, or at least that's how I learned to write this. For example, for the group GLNR, my K is going to be SON of C. And for the Lie group SLNC, well, I complexify SUN, I get SLN. And as a subalgebra of G, this is a diagonal copy of SLN. And finally, later on, I will need to consider the orthogonal complement of small k inside of small g. For example, in the SLNR example, k is SONC, and its complement is just symmetric matrices in SLN. Okay? So now I want to explain two basic ideas that people use to study unitary representations. And the first idea is to make the problem algebraic. When we talk about unitary representations, it involves a Hilbert space, so it has something to do with analysis. And you may want to try to get rid of this analysis in the problem. I will need the following standard notation. U of G is going to be...
I'm sorry, I've got a question. So K, you said, so you first complexify, then you take the maximal compact.
No, K sub R is a maximal compact in G sub R, and then I complexify.
Yeah. So, sorry, you first complexify the Lie algebra,
No, K sub R knows nothing about the complexification. It lives inside of G sub R.
Okay, you take the okay. You first take the maximal compact in the real Lie group, then you complexify. You complexify what? You complexify
this maximal compact.
The maximal compact. Okay, but the maximal compact is going to be. So that's okay. So you started with the semi-simple group. You complexify the maximal compact, and you view this inside
of the complexification of the initial Lie group.
And you look at the algebra of that one. Okay. And then you take the orthogonal complement. Okay, thanks.
Yep. So, so the first thing that I'm going to discuss is algebraization of this problem. And this goes back to Harishchandra in the 50s in a series of papers. So Harishchandra defines the notion of a GK module. Okay? And so what this is, it's a finitely generated module over the universal enveloping algebra, such that the action of the Lie algebra small k is locally finite, meaning that every vector is actually contained in a finite dimensional subrepresentation for this k. I can write this down as so. Okay? And then the second condition is that the action of this Lie algebra integrates to the action of the corresponding group. Right? An important special case here is when the initial group was complex. And so here we arrive at the notion of a Harishchandra G times G slash G module. And I can think about this in kind of a more, maybe somewhat better and more suggestive fashion. I can think about this as a bimodule over U of G. So it's a left module over the left copy of G and the right module over the right copy of G. Okay? And then this Harishchandra condition, this condition here, translates to the following. I can consider the adjoint action of the Lie algebra on my bimodule, just by the familiar formula. And I require that it integrates to the action of the group. And in this case, the terminology is Harishchandra bimodule. And it's easy to give an example.
Excuse me, I don't quite understand how is it a special case, because you had first the compact group on the right, And now G, which is not compact, right?
So this K is a complexification of the maximal compact.
Oh, I see. Okay.
Yeah, it's a complex algebraic group. So now an easy example is U of G itself, which you view as a regular bimodule. It's easy to see that the adjoint action of the Lie algebra on U of G just integrates to the group. Now, what does this have to do with unitary representations? I say that a Harish-Chandra module.
I'm sorry. So,
Yes.
so can you give an example? So in the special example you just gave, this fits into the example that you had before when you had
Yeah,
SU. So this was now, so K was capital K was SUN.
Capital K without subscript was SLN. Okay.
Capital SLN.
Yep.
Okay.
So just kind of this SLN case is a special case of this general construction.
And it is this in this case, how can we describe this universal enveloping algebra?
I mean,
it's abstract.
Yeah, I mean, you kind of, you know the basis, and that's kind of that's more or less about it.
So there is no like really explicit description of that. It's still standard. Okay. Okay, thanks.
So now I say that a Harish-Chandra module is unitarizable if I have a positive definite Hermitian form that satisfies the following invariance property, that the real part of my Lie algebra G acts by skew Hermitian operators. And the intuition that, if you want your group to act by unitary operators, the Lie algebra is going to act by skew Hermitian operators. Now, a theorem of Harish-Chandra actually states that unitary representations of G sub R are in initial bijection with irreducible, unitarizable GK modules. And let me explain how this correspondence works. So let's say that I start with an irreducible unitary representation V. Inside, there is a notion of a C infinity vector, which I'm not going to define, but people can try to guess what that is. This is stable under the subgroup. That can be shown to be a dense subspace. But importantly, since your vectors are smooth, the Lie algebra is now going to act on them. So you should think that V kind of consists of some L2 functions, and you cannot differentiate an L2 function and get an L2 function. But you can differentiate a C infinity function and get a C infinity function. So this is still too large. Inside, I'm going to take the subspace of all vectors where the original compact, maximal compact, acts locally finite, meaning vectors which sit inside a finite dimensional subrepresentation. And this turns out to be an irreducible Harish-Chandra module, and it's unitarizable. Because if your group acts, well, very roughly, if it acts by unitary operators, the Lie algebra is going to act by skew Hermitian operators. And to go back, you just complete with respect to the metric. And it's a non-trivial theorem that these two operations give you this bijection. And so what this buys you is that you make the problem completely algebraic. Okay? Now, since the work of Harish-Chandra, people have learned several ways to classify the irreducible GK modules. And it's known when such a module has a non-degenerate Hermitian form. That's relatively easy. However, the question when this form is positive definite turns out to be really hard. And there are answers in various special cases, but no answer in general. And in many situations when the answer is no, it's very complicated. So this was theorem of Harish-Chandra, some kind of Gaga principle. I wouldn't say so. I mean, it's just, I think that's a result of a different nature. So now comes the second key idea which is due to Alexander Kirillov in the 60s now. And a kind of my description for this idea is that this idea of quantization. So let me explain what Kirillov did. Consider our original Lie group. It acts on its Lie algebra by a joint representation, and therefore acts on the dual by the coadjoint representation. And in particular, I can talk about orbits for the section, which are called coadjoint orbits. And a famous result of Kirillov, which was his, I think, candidate of science thesis and also doctor of science thesis, is the result called orbit method. So in my question, I cared about semi-simple groups, but let's assume that our group is nilpotent. And that's a very essential condition. Another condition that I need to impose is that the group is simply connected. Under this condition, the unitary irreducible representations of my real Lie group turn out to be in bijection with a coadjoint G orbits. And this bijection is natural in some sense. So starting from a coadjoint G orbit, you can construct an irreducible unitary representation. And it's worth noting that, the coadjoint orbits for the nilpotent groups are not particularly pleasant. There is no kind of nice classification in most cases. However, that's kind of an object of conceptually easier nature. So you can view this as a classification of irreducible unitary representations. Now, that's kind of a good news, and the bad news is that if your group is semi-simple, this is not true. And we already see it in the compact case, where the set of orbits is uncountable, and the set of irreducible unitary representations is countable. It's just finite dimensional irreducibles labeled by highest weights. And to this day, there is no precise analog of orbit method for real semi-simple groups. Okay? And kind of, you can think that one of the goals of this lecture is to explain what is known in this direction.
So I'm sorry. Can you explain? So how do you understand a coadjoint orbit? So it's a function on the Lie algebra, and you look at its. Can you give an example, for instance, in your favorite case, SLN?
Well, SLN won't fit.
It's not nilpotent, but at least you've still got a coadjoint orbit.
Well, yes, this is easy, and in fact, for a semi-simple group, there is no difference between adjoint and coadjoint because you can identify these two representations using the Killing form.
Okay.
And the adjoint orbits are known very classically and studied in kind of basic linear algebra courses. This classification is given by the Jordan normal form theorem. So for semi-simple groups, the set of coadjoint orbit is highly structured and is known in all cases. But the point is that for nilpotent groups, this is kind of nasty.
So for nilpotent groups where we know that they correspond to the unitary representation, irreducible representations, it's nasty. But when it's nice, it's too small to be. Okay, I see.
Yeah, that's life. That's usually how life works. Okay. All right. So now I mentioned the word quantization, and I need to explain what the theorem has to do with quantizations. So for this, I need to introduce the notion of a Hamiltonian manifold for my Lie groups. So strictly speaking, that's a triple X, omega, and mu, where X is a C-infinity manifold. Omega is a symplectic form on this manifold, meaning that it's a two form, which is closed and non-degenerate. And I want it to be invariant for the action of the group. I should mention that my group GR acts on X. So I can talk about invariant forms. And on the other hand, if I have a non-degenerate form, I can invert it. I will get a bivector. And the condition of being closed translates into the condition that this bivector gives me a Poisson bracket. meaning a bracket satisfying the Jacobi identity. Now, finally, I have this mu here, and mu is a so-called moment. So by definition, it's the following. It's a map which from my X to the dual of the Lie algebra, which is equivariant and which satisfies the following condition. I can consider the pullback map in the opposite direction. It will take an element of my Lie algebra and produce a C infinity function. And then I can take a bracket with this function. This will give me a derivation of the algebra of C infinity function on X. And I want this derivation to be the vector field which comes from the action. Once a Lie group acts on a manifold, you have a homomorphism from the Lie algebra to the algebra of vector fields. So I have two ways to produce a derivation from Lie algebra elements, and I want these two derivations to coincide. This is what it means to be a moment map. What are examples of Hamiltonian manifolds? It turns out that coadjoint orbits are an example. Namely, it's known after Kirillov and Constant that every coadjoint orbit carries a natural symplectic form. And in fact, this form is characterized by saying that the inclusion of the orbit into G star is a moment map. There is a unique such form. And you can do an exercise and write it down. So coadjoint orbit is an example of a Hamiltonian manifold. So we are getting closer to kind of Kirillov's result. There is a more general class of examples, slightly more general, namely if you have a Lie subgroup in the stabilizer of a linear function such that the quotient is discrete, then I can consider the map from this homogeneous space GR mod H to the coadjoint orbit, and this map is a cover. In particular, I can take the constant Kirillov form and pull it back under this map. I will get a symplectic form, which is invariant, and the section is Hamiltonian, namely I can map from X first to the orbit and then include the orbit into G star. So this should be G star sub R.
Sorry, and this quotient is, which is discrete, it is usually infinite or finite?
So for a Lie group, you can have something infinite, but if it's an algebraic group, then it will be something finite.
By the way, do you mean
algebraic
here the
complex
quotient? And do you mean here the quotient probably based
just as Lie groups?
Yeah, but should it be stabilizer by H or H by stabilizer? Stabilizer is larger.
Good point. Thank you.
Okay, thanks.
Yeah, H is smaller, so yes, in this direction. Now, here are two important observations. So first of all, it's an easy exercise to show that any transitive Hamiltonian action is of this form. Okay, so here I actually described all Hamiltonian actions which are transitive. And second, it's less clear, but it's a nice exercise in exponential map to see that if your group is nilpotent, so actually every coadjoint orbit is already simply connected. And so there are no proper covers. So turns out that in Kirillov's theorem, the kind of the classical object is all transitive Hamiltonian actions. So, and here the notion of quantization naturally appears. So there is this notion of geometric quantization. And so what it seeks to do, it seeks to start with a symplectic or maybe more general Poisson manifold and naturally produce from it a Hilbert space. And you hope that this construction will preserve symmetry. Namely, if on a symplectic manifold you have a Hamiltonian action of G sub R, you hope that G sub R will act on V by unitary transformations. Okay, that's a hope. And there you can further hope that minimal, namely transitive Hamiltonian actions, will lead to minimal, namely irreducible unitary representations. And Kirillov's theorem tells you that if your group is nilpotent, then this works. And moreover, this exhausts all unitary irreducible representations. However, in general, this hope is just too naive. Doesn't work. And yet another point of this talk, we kind of get closer to kind of the actual mathematical content, is that this correspondence work much better if instead of this difficult geometric quantization, we deal with easier algebraic quantization. And that's what I'm going to explain next. But first, let's see if there are questions.
So what is this Hilbert space in the nilpotent case?
You start with an orbit and you produce a representation. And the way how you do it, an nilpotent orbit can be what's called so-called polarized. You got some subgroup in G sub R, and then you use unitary induction from a one-dimensional representation of the subgroup to the entire group. Representations of groups usually can be induced. And it's so in this context as well. But it's very, very special for nilpotent Lie groups. It works somewhat more generally, but you need to have special conditions, and it's kind of, it doesn't give you many, if not most interesting unitary representations. All right. So now we can forget about unitary representations, and we'll go completely algebraic. And the first thing here is to talk about quantizations and their representations. I need to explain what I mean by quantization. And first, I need to explain what is it that I quantize. So I start with A, straight A. It's a finitely generated commutative algebra over the complex numbers. And I wanted to come with two additional structures. First, I want it to be graded. It's decomposed into direct sum of subspaces indexed by non-negative numbers, so that when I multiply an element of degree I and an element of degree j, I get an element of degree I plus j. And I additionally want that in degree 0, I only have scalars. And then I want my algebra to be Poisson. I want it to come with a Poisson bracket. And I want these two structures to be compatible in such a way that the Poisson bracket decreases the degree by 1. So here is an example. I can start with a finite dimensional Lie algebra G and form its symmetric algebra. It has unique Poisson bracket that on the Lie algebra itself, it coincides with the Lie bracket. And then I can extend this bracket by Leibniz identity. For us, we care not about this example as such, but about closely related example. So now I want to take a semi-simple algebraic group over C, denoted by G. And as I've mentioned, G and G dual are identified via the killing form. So there is no difference. I can consider an orbit of the adjoint action. Let's call it O. And it's a smooth symplectic variety. Not just a manifold, it's a symplectic algebraic variety. And then I can form its algebra of regular functions. Okay? This is a Poisson algebra. So this part is fine. One can prove that this algebra is finitely generate. There is a little caveat because your variety is not affine. It's only quasi-affine. And if you have a quasi-affine algebraic variety, then the algebra of regular functions may fail to be finitely generated. However, in this case, this is so. Okay? We have a finitely generated algebra, and in general, this algebra is not graded. It fails to have any initial grading. It's only graded when your orbit O is nilpotent. Okay, and it's a very important notion for this talk. So what does this mean? It means that every element in my orbit is an nilpotent element in my Lie algebra. I don't want to give a definition, but many semi-simple Lie algebras are classical, and there being nilpotent just means being nilpotent as a matrix. Okay? And it's not a very difficult exercise, and I want to give you this exercise just for SLN, to show that all nilpotent orbits are preserved by the scaling action of one-dimensional torus. If I multiply an nilpotent element by a scalar, this element is conjugate to the original. And for SLN, this is just consequence of the Jordan normal form theorem. And once I have an action of a one-dimensional torus on the variety, it gives me a grading on its Lie algebra, on its algebra of functions. And that's exactly the grading that I need. So let's do a very baby case. And for this talk, baby cases have to do with Lie group SL2C. There are two nilpotent orbits. There is a boring nilpotent orbit 0 and an interesting nilpotent orbit which is non-zero. It looks like this. Non-zero matrices with determinant 0, right? And then you can show, using basic algebraic geometry, that the algebra of regular functions is just a quotient of the polynomial algebraic matrix coefficients by the relation a squared plus bc equal to 0. That's formula for the determinant, essentially. It's graded, where the degrees of the variables are equal to 1. And it has a Poisson bracket that can be described in several ways. One of them is to realize that this algebra here embeds into polynomials in two variables, where a goes to xy, b goes to x squared, and c goes to minus y squared. The relation that a squared plus bc equals 0 is satisfied easily. And on the algebra of polynomials, I have the most classical Poisson bracket given by this formula. And the subalgebra of even polynomials, is stable under the bracket because the bracket decreases the degree of a polynomial by 2. This example of functions on nilpotent orbit, can be generalized. Namely, I can take a cover G mod H, and this should perhaps be denoted by, sorry. So H is a stabilizer of my nilpotent element, and I can take a finite index subgroup. Let's call it H0. And then forms a homogeneous space G mod H0. It's kind of a version of an example of a Hamiltonian manifold that I gave before. You get a Poisson algebra, you can show it's finitely generated, and one can actually lift a grading from O, the torus action from O to O tilde by paying a little bit of a price. You need to actually kind of rescale the section. And your algebra is going to be graded by 1 over 2z instead of z. That's like minor technical point that I don't want to dwell too much about. Just let me give you a special case. It's the baby case from before. So I take this nilpotent matrix, and its stabilizer is disconnected. It's all matrices of this form, where the diagonal entry epsilon is plus or minus 1. In particular, I have an index 2 subgroup. And the quotient, the homogeneous space, is just C2 without 0. The functions are polynomial functions in two variables with standard bracket. And if I want this bracket to have degree minus 1, I need to declare that the degrees of the variables are equal to 1 over 2.
And sorry, what does it mean that the degrees are 1 over 2?
It's just, you know, instead of grading by integers, I grade by half integers. It's slight generalization of the setup that I had at the beginning.
Ah, okay.
Or I can grade by integers, and I will need to require that the degree of the bracket is -2.
Ah, okay, I see. Okay.
Yeah, it's kind of, it's a bit annoying, but it's a very minor.
Okay, thanks.
So I will care about the algebra of polynomial functions on such covers, and I will need the so-called fielded quantization. So let me explain what this means. I start with an associative algebra that I'm going to denote by curly A, and I want it to come with algebra filtration. So previously I had gradings, now I want algebras to be filtered, meaning that I still have the notion of degree, but I no longer have homogeneous elements of given degree. And to mirror the condition on the Poisson bracket, I want the Lie bracket on my algebra to decrease degree by 1. Okay? Then I can form the associated graded. It's essentially the same vector space, but I forget everything about the product by the top degrees. Formally, it's defined like so. And this is the graded algebra, which has an initial Poisson bracket by top degree of commutator. Namely, if I take two typical homogeneous elements, A plus elements of smaller degree and B plus elements of smaller degree, the bracket is defined as a bracket of A and B, the Lie bracket, which makes sense in the associative algebra. This has degree less or equal than I plus j minus 1. And then I add elements of smaller degree. And I get a bracket of degree -1. That's how I pass from fielded algebras to graded Poisson algebras. And by definition, a fielded quantization of the graded Poisson algebra A is a fielded algebra A as above, and a graded Poisson algebra isomorphism between the associated graded of curly A and straight A. Well, this sounds abstract. What does this mean? I start with an algebra with commutative product. Okay? And commutative product was graded. I want to deform it just by adding degrees, elements, kind of components of smaller degree to the product. Okay? So I make this deformation, and this gives rise to a Poisson bracket on the initial algebra A by looking at the top degree of the Lie bracket. And I want this new Poisson bracket to coincide with the old one. Okay? So examples. U of G, the universal enveloping algebra, is a fielded quantization of S of G. And the isomorphism between associated graded of U of G and S of G is just comes from the Poincaré-Bergov-Witt theorem. We have this isomorphism, and then it's easy to check that it's an isomorphism of Poisson algebras. Now let's do a bit more complicated example. Let's assume that our Lie algebra G is semi-simple and consider the nilpotent cone, namely the subvariety of all nilpotent elements. The group is going to act with open orbit called principal. And the algebra of functions on this orbit is the same as the algebra of functions on the nilpotent cone. For SLN, principal orbit is just a single Jordan block. It's kind of generalization of the examples that we have seen. Now, to construct quantizations, I need some notation. H is going to be a Cartan subalgebra, and W is going to be the value. And then a classical result of Harish-Chandra identifies the center of the universal enveloping with W invariant functions on H dual. Okay. So now what I can do, I can take lambda, an element of H dual modulo W. It gives rise to the maximal ideal in the algebra of invariance, and therefore in the center. And I can mod out this maximal ideal. UG times M lambda is a two-sided ideal in U of G. I take the quotient. I get a fielded algebra with filtration induced from PBW filtration. And it turns out to be a fielded quantization of functions on the important column. For example, if my G is SL2, then the center is a polynomial algebra in a single element called Casimir. Here I normalize it to be h plus 1 squared plus 4fe. And my quantization is of this form. I just mod out by Casimir equal to some number, which I denote by lambda squared, where lambda is an element of the Cartan, and then lambda squared is a function on the quotient of Cartan modulo W.
Excuse me, in which place did you invoke this principality when you chose the lambda?
So this only serves as a quantization of the functions on the principal nilpotent orbit.
Mm.
So for other orbits, constructing quantizations is more difficult. I just want to give a simple example. So now let's do a cover, C2 without 0. And then the algebra A is just polynomials in 2 variables. Its quantization is a so-called fast while algebra. I take a free algebra in 2 variables, x and y, and mod out the relation that the bracket of y and x is equal to 1. Okay? This is a quantization of polynomials in 2 variables with the standard bracket. And then in a couple of minutes, I think we should do a break. Before we get there, I want to explain what is it that I want to do in this setup. Okay. So first of all, why would we care about these quantizations? So let's take a cover of an important orbit O tilde, and it has a moment mapped to G star. Okay. First, I project to O, and then embed O into G star. And dually, this gives me a Poisson algebra homomorphism from S of G to my algebra A. Okay, it's a G invariant graded algebra homomorphism. Turns out it's not very difficult to show that it leads to a G equivalent fielded algebra homomorphism from U of G to A. And it's called quantum comoment map. Let me just justify this by example. So in example 1, I produce my quantization as a quotient of U of G. So by the very construction, it will admit a map from U of G. And that's the map that I want. And in particular, if I have a module over A, I can view it as a module over U of G by pulling it back under this homomorphism. And so I can hope that interesting module over this, or modules over this A's will give me interesting modules over U of G. Maybe even interesting Harish-Chandra modules. So here is a roadmap. And that's the rest of, mostly the rest of part 2 of the talk. Is first, I want to classify filtered quantizations of these algebras. So this is completely done. Then I want to classify certain nice modules over this A. And the modules can be described informally as quantizations of singular Lagrangians. Maybe in the end of the talk, I will explain what I mean by this. And so the reason I care about it is that potentially these modules will contain all unitarizable GK modules in the case when my group is quasi-split. So split groups are fine. Complex groups are fine. Compact groups are not fine. For compact groups, this is not going to work. So if you have a more general group like, SLN of H, there will be more unitarizable modules than what this construction produces. This classification is done in some cases, but not in general. And finally, we need to decide which modules in 2 are unitarizable. In this case, there is some work in preparation, which maybe I will mention in the very end, which establishes an important result in this direction, but generally, all unitarizability questions are hard and very little is known here. All right. I think it's a good time for a break.
Yep. Thanks. Let us thank the speaker for the first part. And yeah, so we have 10 minutes break, right?
Yep, like up until 1 p.m. and I'm happy to answer questions.
Part two, just a quick question. Is there a path? You said it's done to some extent. So is there a path to the completion, or it's sort of unclear how to proceed after some examples?
These are not examples, these are certain cases. And so basically, hopefully I will have time to explain this. So I'm talking about singular Lagrangian subvarieties. In particular, they will have singularities. And so basically what is done is when the singular locus has codimension less or equal than 2. And one singular locus has codimension 1, this presents serious conceptual difficulties. But for complex groups, for instance, the singularities always have codimension 2. So this case is fully done.
Great. Okay, and we'll talk more about it in the second half.
Yep.
I was just curious.
Yep.
Okay.
Thank you. So we restart at 1 o'clock?
Yeah.
1 o'clock Eastern time and on the hour in 9 minutes.
Yep,
Yeah.
that's right.
Yeah.
Great. I'll refill my tea.
Hello.
Yep.
I've got a naive question. It's
Sure.
so here you're trying to classify the unitary representations of your groups in terms of these graded algebras which generalize coadjoint functions. I mean, functions on coadjoint orbits. Is that what is that right?
So there are
Trying to make a correspondence.
There are two parts. So geometric quantization seeks to start with an orbit and produce a representation in unitary representation. In the algebraic situation, you kind of split this problem in three parts. So first, you want to produce an algebra which is going to act. And these algebras are assigned to these equivalent colors. Okay? And they arise as quantizations in the sense that I explained of algebras of regular functions. So there's just an algebra which acts. Okay? Then I will need to produce certain representations of this algebra, labeled by some additional data.
Okay, so for instance, okay, and then you want to decide which one are unitarizable. So, so how will this relate, for instance, in the known cases where we know, for instance, in SL2R with the principal series and all that, where we know the representations? So this should give, instead actually of describing the representations, it will actually describe more the A modules. I mean, it's going both way, right? Because saying I've classified them by another object, which is maybe more or less complicated. It depends on the situations. It's going both ways. So it's not really a classification. It's more of a correspondence. And so how would this correspondence, what would it give for SL2?
For SL2R, for any group, we seek to parameterize Harish-Chandra modules. And once you have a Harish-Chandra module, getting a unitary, once this Harish-Chandra module is unitarizable, getting an actual representation of a group is kind of easy. You just complete and you've got a representation. So the real question is to solve this algebraic problem. And I should say that, with Alex, we had this brief discussion. For this kind of techniques, SL2R is a bad case, even though the unitary representations are known very classically. In some sense, this technique will allow you to produce much more interesting representations, but in a different case. I will talk a little bit about that setup later on. I'm not sure to which extent this is an answer, but that's what I can say. Is this does sound good?
Okay, thanks.
So the problem with SL2R is that this Lagrangian subvariety in question is just a union of two lines. As such, it has singularity in codimension 1. This is kind of a bad case.
Can I ask a naive question? I've heard about another context where the quantization is mentioned is the formation of UG quantum groups and things like that.
Yep.
Is this related here?
Nope. So for me, U of G is already a quantized object. And if you pass to quantum group, what you do, you additionally quantize the coproduct. And that's not something that I want to do.
Mm-hmm.
All right, shall we continue? Okay, so this is a roadmap, and I'm just going to tell you what is known about 1 and 2, and maybe if I have time at the end, I'll talk about 3 as well. So classification of quantizations is done, and it's the following theorem. I start with cover of an important orbit, O tilde. I get this graded Poisson algebra A. And then the claim is that there is a finite dimensional vector space depending on this A. I will call it H sub A. And a reflection subgroup, crystallographic reflection subgroup in the group of linear operators on HA, such that the fielded quantizations of A up to isomorphism are in bijection with the quotient of H mod A by W of A. And that's an affine space. Okay. So example, if my algebra A is functions of an important cone, then not surprisingly, this H sub A is essentially the cartan of G, and W sub A is the Weil group. And the correspondence work as follows. I take lambda in H mod W and produce that algebra A sub lambda, which is a quotient of U of G modulo the corresponding maximal ideal in the center. So that example gives you a complete classification of quantizations in this setup.
Sorry,
Yeah.
in this case, this in general, W sub A, is it the subgroup of W of the Weil subgroup?
It's a subquotient.
It's subquotient.
So H sub A is a subspace in cartan, and W sub A is essentially it's a subgroup of the normalizer of this subspace by the centralizer or something like this.
Should it be always finite?
Yeah, it's a finite.
It's always finite. Okay.
Yep.
Thanks.
It's like you take a parabolic subgroup in your Weil group, and then you form the normalizer and mod out by the subgroup. And then W sub A will live inside of such.
Okay, I see. Thanks.
Now, there is a very easy example where I take the algebra of polynomials into variables with a standard bracket. And in this case, there is just one quantization. So this H sub A is 0. And this quantization is the first Weil algebra. So that's a little bit technical remark, but let me tell you something about how the theorem is actually proved. So I formed the affine variety corresponding to A. So A was functions on a non-affine variety, then I can take the affine closure. And this is the X. This closure is singular, as we already see in the example of the important cone, but it's so-called singular symplectic. It's a very nice kind of singularities. That's a notion introduced by Boville more than 20 years ago. And what it means is that my X is normal, and the Poisson bracket is not degenerate on the smooth locus. So the smooth locus becomes a symplectic algebraic variety. Let omega rec denotes this form. And then the main condition is that there is a resolution of singularities of X, let's call it Y, such that omega rec extends to a regular form on this Y. This extension is automatically closed, but may fail to be non-degenerate. And the nice property is that once there is such a resolution, then this is true for any resolution. Okay? So then, some like 15 years ago, there was this big advance in birational geometry due to Berker, Cassini, Heiken, and McKernan, which established existence of so-called terminalizations. And what it gives in our setup is that there is a maximal partial resolution of X, which I will call X tilde, which is still Poisson. So this Y here will not be Poisson because the form may become degenerate. But then there is a partial resolution such that it's maximal. Okay? And it's an example of this terminalization. And in the special case is when my X is an important cone, then X tilde is a so-called Springer resolution. It's a cotangent bundle of the flag variety. And what I can do in this case, and in fact in general, I can take such X tilde, take the regular locus and take the second cohomology. This is a space H sub A that I've mentioned. And once I pick an element, lambda tilde, I can produce a filtered quantization now of the structure sheaf of X tilde. I don't want to explain what this means. Some sheaf of filtered algebras on X tilde. In the case of the Springer resolution, I just take the sheaf of twisted differential operators. And I can take the global sections. That's the construction of this algebra. So all these shapes d lambda tilde are different, but the global sections may be the same, and this happens precisely when the parameters are conjugate by the elements of that reflection group. And so that's how I can construct quantizations in general. And so it's kind of, you see that that's a very implicit construction. Now, the classification result has a very nice consequence, which I would like to call algebraic orbit method. So the original orbit method gives you a bijection between the classical side, and the classical side is like this transitive Hamiltonian actions, and the quantum side. The quantum side is irreducible unitary representations. In our situation, we still have a bijection, and the classical side of this bijection is the same as before. So I consider all equivariant covers of all coadjoint orbits, which is the same as all transitive Hamiltonian actions up to isomorphism. But then the quantum side I replace with its algebraic counterpart. I consider all filtered quantizations of all equivariant covers O tilde of all nilpotent orbits. So in the classical setup, I have all coadjoint orbits, but in the quantum, I only consider all nilpotent orbits. Then I take all covers and I take all quantizations. And it turns out that these two sides are in natural bijection. And that's a consequence, more or less, of this theorem. A remark is that the way how this works technically is that I can identify the classical part with another kind of deformations, namely the filtered Poisson deformations of all covers of all nilpotent orbits. And then you can ask, okay, so in the classical side, I also have covers of nilpotent orbits. Where do they go? It turns out that they go to quantizations with parameter 0. These are quantizations which are called canonical. They're important from a certain point of view, which I may have time to explain. Meanwhile, other questions?
So altogether, you no, sorry, no, maybe I'll ask later.
Okay.
Sorry, maybe.
I actually
So now
wanted
that's
to,
kind of that was
sorry,
the first.
Sorry, yeah, I wanted to ask. You said that we can do deformations of the symplectic form, right? That was the deformation.
Here.
Yeah. So how many?
Rather the Poisson
of
bracket,
this?
yes.
Yeah. Yeah. Okay. So how many of these deformations do we have?
The same. Where is it? Yep. So it's the space.
Ah. Okay. So basically, it's not just like one, but it is kind of pretty.
So an important thing is that
amount.
it's not that I just deform the bracket on a given algebra, I also deform the algebra itself.
Mm-hmm. Okay.
And so somehow you should think that if I take an arbitrary cover, then the algebra of functions on this cover has filtration, and the associated gradient will be the algebra of functions on some nilpotent cover. That's how it works.
Okay, thank you.
All right, so classification of quantization was the first part in the program. Now I need to classify certain modules over these quantizations. And I start with a setup of a complex group, where my modules are actually bimodules, with Harishchandra bimodules. the result gets a bit technical, so I'm going to make some simplifications. So I start with some orbit O, nilpotent orbit, and I want to take its Galois cover. What does Galois mean? That means that the quotient of this cover by its group of automorphisms is the original orbit, and not some bigger cover. That's a technical assumption to simplify the statements. So I take this cover O tilde. And then let me remind you that if I have a quantization parameter, lambda, I can produce a quantization. And it comes with a homomorphism from U of G to the quantization. Now, what I want to consider is the kernel of this homomorphism, which is a two-sided ideal. Okay, which I will call I lambda of O tilde. And I can form the quotient of U of G by this two-sided ideal. I will call it A lambda prime. It's a subalgebra in A lambda. A bit later, it should become more clear why I will want to do this. And in fact, one can show that the image, the subalgebra is constrained. It's constrained by the following. I can consider the automorphism group of my quantization as a fielded algebra. It's a finite group. And let me denote it by pi lambda. Turns out that the image of U of G is always invariant under this group. So in fact, A lambda prime sits inside of invariance inside of A lambda. I'll give some examples a bit later. Okay. And now I'm going to assume that the two-sided ideal that I defined from my quantization is maximal with respect to inclusion. There is a classification theorem in a more general situation, but this sort of simplifies the statement. So now you can ask, when does it happen? And it's a theorem, actually it's a fairly hard theorem, which was proved by myself and Lucas Mason-Brown and Matveevsky in many cases, and then Lucas and Mitya completed it in the remaining cases. It turns out that when the parameter is 0, that's of special significance, then this maximality condition holds. And moreover, this maximality condition implies that this image of U of G coincides with the invariance. So now I want to talk about Harishchandra A lambda prime K modules. And what I mean by this is that I have GK modules, which are annihilated by this idea. And similarly, I can talk about A lambda prime bimodules. That's my current focus. And we have the following classification theorem. So I have this cover O tilde, and I have the finite group pi lambda. In fact, well, it acts on the quantization, therefore it acts on the associated gradient, therefore it acts on O tilde. And I can take a smaller cover, which is a quotient of O tilde by this group. When lambda is equal to 0, what's going to happen is that this O hat is actually the initial nilpotent orbit. Then I claim the following. There is a normal subgroup, which I call gamma lambda, inside of the fundamental group of O hat. So both are finite groups, and this gamma lambda is normal, such that the category of Harishchandra A lambda prime bimodules is very easy. It's actually the category of representations of the quotient. So this complicated, a priori complicated category of bimodules is equivalent to the category of representations of some finite group. And in fact, what's so special about bimodules is that you can tensor them. So this is a monoidal category. Well, of course, this is a monoidal category as well, and this equivalence is monoidal. And moreover, I can compute gamma lambda in some combinatorial terms. So I have a complete description of what this category is. So now the question is how to think about this result. There is actually some geometric meaning. So the representations of the fundamental group is essentially the same thing as local systems on O hat. And for me, a local system is a vector bundle with a flat connection. Now, if you have a Harish-Chandra bimodule, it's a quantum object, and you can take its classical limit in a certain sense. In particular, the classical limit will essentially be a local system on this cover. And that's how I can pass from a Harish-Chandra bimodule to a local system, aka a representation of the fundamental group. And this is what gives me this equivalence of categories. So now kind of let me give you some examples. So let's assume first that this O hat is O principal, the principal nilpotent orbit. And let's assume that lambda is 0, the canonical quantization. Then it's not so difficult to show that gamma lambda is pi 1 of O. What does this mean? Is that it means that I have only one irreducible Harish-Chandra bimodule. And what is it? It's a regular bimodule. So here the classification is trivial. Now let me give you the simplest example when I have a non-trivial classification. And that's for G equal to SL2. The cover in question is still the principal orbit, but now the parameter lambda is 1 over 2. And there is something very special happening at this particular parameter. Namely, I can construct a lambda very explicitly. I start with the first Weil algebra, which I call A tilde. That's a quantization of a twofold cover. And on this Weil algebra, I have the action of the fundamental group of my orbit. So my orbit is quadratic cone without a point. The simply connected cover is C2 without a point. And the whole fundamental group is Z mod 2Z. And it acts on the Weil algebra, where the non-trivial element sends x to minus x and y to minus y. Okay? And I can take the invariance for the section. It turns out that this invariance is exactly that quantization I have started with. And what I need to tell you is how I can pass from a representation of Z mod 2Z to a bimodule over this algebra. Well, the recipe is I take A tilde, I tensor it with my representation of Z mod 2Z, and then I take invariance. And this defines for me a monoidal functor from representations of this group to the category of bimodules. This monoidal functor turns out to be an equivalence. And this is sort of a general story. If your quantization A lambda prime is invariance of some group, finite group in some quantization of a cover, then I will have a functor from representations of gamma to bimodules over this thing by the same formula. And that's essentially how, well, I mean, it's kind of, it's an important step in the kind of in general construction of this equivalence. One can deal with a case when the ideal in question is not maximal, but let me maybe skip it for now. I mean, we still have an analog of the theorem, but it gets a bit more complicated. Other questions? So, the theorem in question handles the case of complex groups. So it's still not a classification of unitary representations, but it's kind of a step 2, understanding interesting models. And now I'm going to tell you 2 things. I'm going to tell you what we know about the more general real case. And I'll tell you kind of a general formulation of the problem. And then maybe I will stop. So, now suppose that my Lie algebra, complex Lie algebra is G. G is simple. This corresponds to simple real Lie groups which are not complex. K is fixed points of some involution. That's how complexifications of maximal compacts are described. Let's call this involution sigma. And before, I didn't really have any restrictions on the orbits that I consider, the orbits that I then quantize. For my result, I will need to put a restriction. And this restriction is the codimension of the boundary of my orbit is big or equal than 4. And this is actually a very restrictive assumption. So namely, what do we have for SLN? For SLN, the Jordan normal form theorem tells you that nilpotent orbits are classified by partition. And one can ask what is the condition on this partition which guarantees this codimension condition double star. Well, the condition is that the parts differ from each other by 0 or 1. So I can write my partition in a decreasing order. And then my condition is equivalent to saying that adjacent parts are either equal or differ by 1. Well, that's some sizable chunk of partitions, but certainly very far from being all partitions. And here we have the following classification result due to myself and Schilling U. So I still assume that maximality, that's not very essential, but I also assume the codimension partition. And the claim is that the irreducible, well, I should say A lambda prime, the same as A lambda, so Harish-Chandra modules are equivalent to the following. So I consider the following variety, or intersection with K part, the complement of K under the Killing form. It turns out that this is a smooth Lagrangian subvariety inside of O. It will have a priori many components, but in any case, I can consider twisted local systems. I will comment on what this means a bit later. With a certain twist, it turns out that my category of modules is equivalent to this category of twisted local systems. So remarks. The twist of a local system will depend on lambda. In particular, for lambda equals 0, I will have half canonical twist. The twist is an element of H2. So what I do, I take the canonical bundle of this Lagrangian subvariety, I take the first Chern class divided by 2. Then the kind of classical result is that O intersection with K perp is actually a finite union of K orbits. And they're all Lagrangians, as I mentioned. Then what are twisted local systems? Well, local systems correspond to genuine representations of pi1, and twisted local systems correspond to projective representations. So it's kind of, it's like projective connections as opposed to usual linear connections. And finally, the mechanism how this correspondence works is similar to the previous theorem. So I take Harish-Chandra module, I take its quasi-classical limit, and this gives me that twisted local system. Any questions?
What exactly is twisted?
So the easiest formal way to define it is the following. So what is a local system? It's a vector bundle with a flat connection. And what is a vector bundle with a flat connection? Flat connection gives you an action of vector fields, and this action then extends to the action of the sheaf of differential operators. So vector bundles with flat connections are modules over the sheaf of twisted differential operators that are coherent over the sheaf of functions. Twisted local systems is the same, but instead of usual differential operators, they take twisted differential operators. It can be twisted, for example, by some line bundle. I take differential operators in a line bundle.
Mm-hmm.
Or you can think about projective connections. So when you have holonomy, and the holonomy, instead of just being kind of trivial, it's scalar.
I see. Thank you.
Okay, and then kind of maybe the last thing that I want to explain, and maybe I can say a bit more during questions. I want to explain the general framework for this kind of classification problems. So what do I have in my examples? I start with X, which is a spectrum of functions on some orbit. It's a singular symplectic variety. And then in both my examples, I actually have some distinguished smooth Lagrangian subvariety in the regular locus. In the bimodule example, I need to replace X with X times X opposite. And this opposite means that on the second copy, I invert the sign of the bracket. And since I do this, then the diagonal copy of X is Lagrangian. And so my Y is just the smooth part of it, the part coming from the orbit. And in the GK case, a bit more generally, I take X itself and then consider O intersection with K part. It's a smooth Lagrangian. And what both theorems do, they try to relate Harish-Chandra modules or bimodules, this is a quantum object, to a twisted local system on Y. This is a classical object. And so it's still some kind of version of an orbit method. And a very important observation is that in both cases that I consider, the codimension of the complement of Y in its closure is big or equal than 2. For example, in the complex group case, this closure is X itself, and X is singular symplectic, in particular normal. And if you have a normal variety, then the codimension of the singular locus is big or equal than 2. So this condition is satisfied. And this kind of guarantees for us that, that's a statement that one needs to prove, is that the quantum object will be uniquely determined by this twisted local system. One just needs to say which twisted local systems actually can be quantized. And in order to determine this, I need to get understanding of singularities of Y closure in codimension 2. And it turns out that in both situations, I understand the singularities. For example, in the diagonal case, well, I have a symplectic singularity in dimension 2, and these are all Kleinian singularities. These are C2 modular finite subgroup of SL2. That's it's a very classical object. So what is the general problem then? Let's say that I start with a singular symplectic variety X, let's call it X hat to distinguish from the previous case, and I have a singular Lagrangian subvariety. I don't define what singular Lagrangian subvariety means, but it roughly means that I have a singular subvariety whose smooth locus is Lagrangian inside of the smooth locus of X. Then what I want to quantize this Y hat with some additional data. And what this data should include, it should include a suitably twisted local system on the kind of the regular locus of this Lagrangian subvariety. And then the result of quantization is a module over A lambda hat. Okay? So I told you two classification results. They were both in this Lie theoretic setup. It turns out that the case of bimodules works generally with a suitable definition. So I can solve this classification problem more or less for any singular symplectic X. And the result is very similar to what we had before. And then kind of the bad news is that if my Lagrangian is too singular, meaning that the codimension of the complement to the regular locus is big or equal than 1, then this poses essential difficulties. And just kind of to give you an idea of what kind of difficulties there are, imagine the following situation. Let's say you have an algebraic variety, X. You have some open subvariety, and on X, you have a vector bundle. So if the complement of that open is of codimension bigger or equal than 2, then you can recover the vector bundle from its restriction. That's Hartog's theorem. But if the complement of has codimension 1, you cannot do it. So that's a difficulty of this nature. All right, and maybe we don't go to part 3 with the scary title, although if people have questions, I may be happy to give some explanation. So let me stop the talk here.
Okay, let us thank the speaker for the great lecture. Are there any questions?
If I'm not mistaken, in particular, you on the twisted local systems, you get some sort of non-symmetric monoidal structure. Is this something familiar?
So I get something monoidal for 2 reasons, roughly. First of all, my local system wasn't twisted. Second of all, it was a local system on diagonal.
Mm-hmm.
And in the general case, so categories of Harish-Chandra modules are module categories over the category of Harish-Chandra bimodules. So in principle, kind of, these are still modules over the Lie algebra, you can still tensor them, but that sort of, it doesn't behave very well. It will violate, for example, finite generation.
So
just tensor them as modules over Lie algebra.
So twisted local systems correspond to Harish-Chandra modules, and to bimodules correspond something else?
To bimodules, I have local systems on the diagonal.
Yeah.
So once I have something on the diagonal, I can kind of convolve with that. And in quantum world, it will be just tensoring a module with a bimodule over the algebra.
Is there a treatment in the style of something called Tanaka reconstruction, when we have this little category which you sort of control, and then you have fiber functor, and then you...
Yes, you can say so, although this is a very, very easy case of Tanakian reconstruction, when in the end of the day, it gets just some representations of a finite group.
Okay.
But indeed, you can think about it this way.
Okay, thank you.
Any other questions?
Maybe I'll ask another one. So if you consider all these lambdas together, I mean, is there some meaningful structure which you could utilize to describe the whole thing somehow?
Yes, so you can consider kind of families of modules. And this may be useful from many perspectives. Like you could, in principle, hope that if your module is kind of nicely deformable, it will be easier to describe them or give a classification of such modules, but it's still kind of difficult. Maybe to make this more concrete. So what happens in the case of SL2R? In the case of SL2R, the variety that you need to consider is just this quadratic cone. Inside of this quadratic cone, you have a Lagrangian, which is, well, your quadratic cone is like something like A squared equal to BC. And then you can consider the variety A equals 0, the union of 2 lines. It's badly singular. But if you deform, if instead of quadratic cone, you consider a quadric, like a squared plus bc equal to some z, where z is a complex number, then in non-zero fibers, what do you see? You see a hyperbola. You see bc equal to z. That's a smooth variety. It's easy to quantize. And then you can try to, maybe take these quantizations and degenerate them. And this is kind of gives you essentially all modules that you need. And of course, in general, there is this question of whether, I have an interesting Harishchandra module which does not deform, and this is unclear. So considering things in families should be great. The only question is whether a given guy actually has a family. Maybe it's an orphan on its own.
I will ask another question, basically from my field, I would say. Can this be applied to this, to the Kazhdan's property T questions, like to determine if a group has this property, which deals with almost invariant vectors?
If only I knew what Kazhdan property T was, I would answer this more meaningfully, but somehow I don't know.
Okay. Okay, thanks. Well, it deals with basically with an implication which says that it has a Kazhdan's property T if an existence of if every irreducible unitary representation having almost invariant vector, it should imply that it has non-zero invariant vector.
So my gut feeling is that the answer is no. I mean, here in this business, so-called spherical representations, meaning representations with a vector invariant under the maximal compact, play a special role. I work with irreducible representations, so typically there will be no vector invariant under the entire group. So that's what I can say.
Yeah, so basically my question was motivated by this idea if one can basically go through the classification and maybe using this, basically what your work does, it essentially gives like another language, right? How to work with unipotent representations. So maybe
unitary, yeah. So I didn't say what
unitary,
unipotent was, and it's these are representations of canonical quantization essentially, where one knows more than the general situation.
Okay. Okay. Thank you. Okay. If there are no other questions, we should thank the speaker again. Thank you very much for the great lecture.
Thank you.
Thank you, guys.
Thanks again for joining us today, and we hope to see you all soon.
Yeah, thanks.
Okay, thank you.
Okay,
Have a great day.
thank you. Yeah, bye-bye.